Hello and welcome to Precalculus. Welcome back to Precalculus because you were here before. The goal for today is to learn about inverse functions. Technically, right, if you want to use those three terms, inverse function is like the undo button on your software, right? You make a little oopsie and you push the undo button and you go back to where you were before you do the oopsie. Now, to understand what inverse functions do is they play the game of input-output and reversing that with the inverse function. So if I have, let's say, the f of 3 give 19. Now, I don't know what that function is. I don't care what the function is. The idea is that the input is 3 and the output is 19. The inverse function will take that 19 and bring it back to 3. And that's exactly what undo button does. So inverse function is the one that it's denoted by this f with the -1 as the exponent. Now, not to be confused with x to the -1, right? Because x to the -1 is 1 over x. That's algebra and has nothing to do with the inverse functions. And that's the problem right off the bat with the notation, because you have inverse function and this do two different things. Bah, right? So let's go and discover what the inverse functions do, represent, what they look like, and the situations where you do not have inverse function. You have an inverse, but you don't have a function. Remember that every equation, right? Not every equation is a function. Some equations are just relations, and some equations are functions. So let's go and think about this. I'm going to put up y equals 3x minus 5. And I'm going to, or I can call that f of x, right? And I'm going to ask you to compute f of, I don't know, 7. Doesn't matter. So that's going to be 3 times 7 minus 5, and the answer is 16. So there has to be, it doesn't have to, but there has to be a method to go back, right? Because I want to find another function that feeds 16 and gives me back 7 on the other end. And the question is, how do we do that? Well, if you carefully observe the first example, do you see how for inverse function input was 19 and output was 3? So what can you tell me? What changed, right, in between the two cases? It's the obvious thing. You just need to say it. If you're thinking something obvious, that's probably it.
They switched
Yes. What switched?
the input and the output.
Beautiful.
First.
Yeah. You switched input with output. And literally that translates as swapping x with y. Because isn't it your input set of all x values, input values, and your output is set of all y values, output values. So you literally switched x with y.
How can you do that though? Like, shouldn't f of 19 be a lot different than?
Oh, f of 19, yes, but this ain't f of 19, my friend.
Oh, I didn't even see that. What is that
Okay,
little
here.
negative?
Is it better now?
Yeah, I see it now.
Okay, cool. the magic of a touchscreen tablet, right? So
Yep.
so I agree completely. F of 19 is, we don't even know what's gonna be, right? But I know that the inverse f of 19 is 3. All right, so we figured.
Oh, I thought it was the inverse of f of 3. Oh, okay. I get it now.
Cool. All right, so let's write this in blood. To find inverse of y equals 3x minus 5, swap x with y, and solve for y. Guys, whatever I write in blood, as I would say, is something that you must know, otherwise doom and gloom and everything else. So we started with y equals 3x minus 5, and then here is the x equals 3y minus 5. This is when the switcheroo happened. Do we all see what happened? So I switched domain and range. I switched domain and range. And as a result, right, I have now this equation here, which I need to solve for y. So move 5 over, swap the sides, divide by 3. I mean, this is rudimentary algebra. And ta-da! There it is! Your inverse. So, this is your function, and this is your inverse. Now, let's test this. How much is f of 2? Well, it's going to be 3 times 2 minus 5, which is 6 minus 5, which is 1. Bueno. How much is the inverse of 1? Well, you should be able to tell me that before I compute it. It's going to be
it should
2.
be 2, right?
Exactly. So plug in 1. 1 plus 5 over 3 is 6 over 3 is 2. So when you plug 2 into the function, you get 1. And then when you plug in 1 into the inverse, you get back 2. Doesn't sound like much, except it drives a lot of our mathematics. It doesn't sound much in this form. Yeah.
Why is the symbol for inverse a -1?
Oh, I've been asking that myself for 30 years, man.
Could it be like, if it was
I
-2,
would
would that
love
mean
it
something
more if it
else?
was like heart or flower or something, but it's not. So yeah.
Is the -1 mean anything? Like, could it be switched out for -2 and mean something else, or
No,
is it just a random symbol that's used?
that's it. It's -1 and you're done. That's the only one inverse function. That's it. There are
Gotcha.
no other, there are no other meanings to it.
I have a question. I understood completely the first part and how we get to x plus 5 over 3, but then I got a little lost with the f of 2 equal. Why do we do that?
There was an example to show that you pick you do some calculation and then you can undo it using the result
Oh,
to
is that
show
how
that
you
it's undo.
Oh, is that how you check to see if they like
No, we're
match?
gonna have a really cool way to check that you might hate, but this is just, let's have fun. Let's do another example. How about f of -10, just because we can. So 3 times -10 minus 5 is equal to -30 minus 5 equals -35. So when we do just computing any function value, which is what we learned the first class, plug a number in, we got 35 as the output. Now, if you use the inverse function on that output, you better get that -10. So -35 plus 5 over 3. Because your inverse function was x plus 5 over 3, right? That was the inverse function. So if you put your output in the input of the inverse, it should spit out the original -10. So let's see. That's going to be, -30 over 3, which is -10. Woohoo! Is it time for us to talk a little bit about the world around us? You take off your sweater and it's inverted, right? If you just pick up the bottom of the sweater and you go hands up over your head, when you get out of the sweater, it's inverted. Is it?
Yep.
Yep. Now, what happens when you invert it again? It goes back into the original one, right?
Yeah, it just goes back to normal.
Mm-hmm. Which means that the inverse of a inverse is the original function. Which would make sense, because if I am to plug this in a function again, I'm going to get negative 35, and then I plug it in back in the inverse, I'm going to get negative 10. You can just go like that forever. It's kind of cool. So, inverse of a function will return the value you had before you did the calculation. And it's literally the undo button. We can draw a pretty little picture over here where we can pick an element, x, map that element into y using the function, and then map it back into x by using the inverse. So this could be your domain, and this could be your range. So the function takes elements from domain into range, changing them. So you can have this function like this. So you feed your input x in there, and then that spits out a y, and then you feed that y into inverse, sorry, and that spits back x. It's like a loop. I don't care which of these diagrams you like better, but what we had, if you look at the example up there, you feed negative 10, function changes it into negative 35, and then you take negative 35 with the inverse, bring it back into negative 10. That's what it is. Now, inverse functions are insanely important for a lot of stuff we have in sciences. Clearly, the easiest and closest to understand that is to like where you would use something like this is like to invert all of the colors on the image, right, in a computer software of some kind. There is a filter, right, that flips out all of the colors. So you put in a colored image and you push that button and it just gives you all the numbers inverted, right? Well, that's inverse function. And if you push the same button again, right, it brings it back to the original one, because the inverse of the inverse is the original thing. Another application, right, as I said, you mess up something on the whatever you're doing on a computer, if there is an inverse button, it brings you back to the original state before you change it. Because 100% of the things that you do on a computer is some kind of function applied somewhere, right? So that's it, right? That's it. So these are the things that we have to understand and use and kind of go through as we go. Now, the question is, does every function have an inverse function? And the answer to that is big no. Does every function have an inverse? The answer to that is yes. And now you go, wait, what? Well, the first time I said, does every function has an inverse function? And the answer was no. Does every function has an inverse? Yes. So clearly there is a difference between inverse function and inverse. Well, yeah, because you have expressions, and some expressions are functions and other expressions are not functions. So clearly, if inverses are expressions, well, some of them are not going to be functions. So you don't have inverse function every time. Sometimes your inverse is a function and sometimes it's not. Now, the title of the lecture is Inverse Functions, but you also have to be aware of the situation where you do not get inverse function, which leads us in a second part of the lecture where we talk about restricted domains and all of these kind of things. So let's dig a little bit deeper into this idea of inverse and then inverse function. The only method that you guys have at your disposal to figure out an inverse function is to swap x and y. That doesn't change. So if you have good old example, y equals x cubed plus 3 plus, I don't want to do 3, let's do 5, right? You are going to say, okay, to find the inverse, I swap x with y. You don't have to write this thing. And you just get x equals y cubed plus 5, which is x minus 5 equals y cubed, which is y cubed equals x minus 5. Hit both sides by the cube root, and y equals cube root of x minus 5. So the inverse function, and I said the inverse function is cube root of x minus 5. Now, why is this inverse function? Because this thingy here is a function. It passes vertical line test and is a function. So this particular function here has inverse function. Passes vertical line test if you draw the graph. Awesome. So now you have a function and inverse function as a pair. So that's great. So this over here is inverse function cube root of x minus 5 passes vertical line test, the VLT.
How are you giving it the vertical line test without graphing it?
Oh, those are my divine powers. I know what all of these graphs look like. In your case, if you don't know what this graph looks like, you're either going to create the graph, or you are by picking those points and figuring things out, or you're going to do the take the calculator and graph it in a calculator. So that's the right, because I know what the graph looks like, so I can just write it down and move along. But if you don't know what the cube root of x graph looks like, this one is clearly, what's the difference between these two graphs, by the way? When I have the vanilla state and this one over here.
One is shifted 5 to the right.
Beautiful. So what I need you to know is this puppy over here. And that's very simple to graph, because you're not going to worry about this because you know it's a shift to the right. That's the power of learning those shifts. So you can quickly, right, since you are wondering about these things, which is amazing, by the way, you say, okay, so all I need to do is to pick x values and compute y values, and I'll know what the graph looks like, right? So pick, okay, I can take a cube root of 0, that's going to be 0, cube root of 1. The next number is 8, because the answers of the cube root will be 0, 1, and 2. So when you draw the graph, you go 0, 0, 1, 1, and then 1, 2, 3, 4, 5, 6, 7, 8, and 2. Oh, wait, I can also take cube roots of negative numbers, because this thing is, the cube roots are okay, right? The odd roots are okay with the negatives. Even are not, because they spit complex numbers out. But the odd ones, right, they're okay. So I'll also have that puppy, that puppy all the way there. So the graph looks like this for my cube root function. And I know that I need to shift it 5 units, 1, 2, 3, 4, 5. So technically goes there, so I don't need this. I need that. Oh, that passes vertical line test. Now, all of these things happen in my head because I've been looking at this stuff for like 15 years, right? So I just move along. You, trying to learn this, have some self-discovery, right, to do, and say, oh, yes, it is a function because it does pass vertical line test, because when you draw infinitely many of these vertical lines, they only cut through function once. So pass vertical line test. And because it passed vertical line test, it's a function. So our problem here has the inverse, and that inverse is a function, so inverse function. Now we're going to contrast that with another friend we have, y equal x squared. Now this friend can also swap x and y because they all can, and you're going to get x equals y squared. Now you're going to solve for y, and we immediately see hell breaks loose over here. Plus minus x. Plus minus root x, I mean. Y equals plus minus root x. Well, if I try to graph this, I know the square root of x. That's my square root of x. But I also know that negative is reflection on the x-axis over here, so the other part is here. That's the bottom
Doesn't
branch.
pass vertical line test.
Ah, it fails vertical line test. This puppy, not a function. Is it an inverse? Yes, it is. But is it a function? No, it's not. So if I put from here an input of f of 9, what's f of 9? Well, it's 81, right? What, now, can I stick 81 in a root and get 9 back? Yeah, I can, which is using this. So there is an inverse, but it's not a function, because there is also negative 81, which is going to give me negative 9. I didn't ask for it, but it's there, and I can't ignore it. So I hope you guys are getting this idea of you always have an inverse, but some of those expressions are going to end up not being a function. And we can fix that by chopping up original function, right? Chopping up its domain so that what's left is a function. And that's called restrictive domain. So I'm going to have my y equals x squared, but I'm going to have that on 0 to infinity. So I technically cheated. What I did is I only took this, come on tablet, this much of my parabola from 0 to infinity. So I'm only dealing with a half of the function. I could have done the other half, but this is the one I picked because I guess it's Thursday. So, blah, 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 swap x and y, blah, 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 blah. All of a sudden we get f of inverse, right, is equal to plus minus root x, but we have to drop the minus. Actually, you know what? Let me write it out because we know exactly where we do the chop. So x equals y squared equals x. Take the square root of both sides with a plus and minus. These guys cancel on this side. And then we did not have the negative part of x squared graph. So we can drop the minus. Therefore, y equals just root x. Now, when you have just root x, that is a function. So now you have inverse function. So that's your root x. This is still your x squared, but it's only half of the domain. And generally, we can always do this for these functions that are symmetric like this on the x-axis, because it's symmetric. So the stuff that we delete, we can easily replace if we need later, but it allows us to have an inverse function. It is a big problem, guys, when you don't have a function. Like, you might go in your head, yeah, what's the big deal, right? Inverse or inverse function, who cares? Calculus cares, because your calculus is done on functions. You will take the limit of the function. You will take the derivative of the function. You will take the integral of the function. So you cannot say, I don't care if I just have an inverse or inverse function, because you're coming up on like 2 years of calculus, calc 1, 2, 3 differential equations. That's 2 years, 4 semesters of calculus. And calculus works on functions. So you can't say whatever, because it's not whatever. And in 2 months, we are going to see that we have another bigger issue, right, than the puny x squared. Because remember this guy? We've seen it. You put the inverse for that. Look at that. That's bigger hell no on a function than cutting it only twice. So we have to figure out what is the part of the sine function. Now, that's the story for another time. But this lecture that you have now in 1.8, we're coming back to it when we learn the exponential function. We're coming back to it when we learn trig functions. You're coming back to it when you learn hyperbolic functions in Calc 2. 1.8 is not going anywhere. It's going to be done over and over and over on any function you ever learn, because this is a property of all functions. They all have inverses, but some don't have them as inverse functions. They just have them as inverse unless you are able to, if you want to think of this as cheating, you don't have a function in the inverse unless you fix the domain using the restrictive domain. Now, how do we detect that the function will have inverse or not inverse function without looking for an inverse first? And that is also a very simple problem to solve. It's called horizontal line test. Ooh. Horizontal line test. Halt. If the other one was volt, this one is halt. So what's halt over here? Well, let's take a look at our two functions from before, right? So we talked about, let's just take plain vanilla x cubed. Y equals x cubed. If you don't know its graph, well, it's time to get busy with a chart of values. If you know the graph, you just draw the graph and you move along with your life. So here's your good old friend x cubed, which had the inverse, we saw it, like this as the cube root of x. Bueno. Now, we go to our old friend x squared, which looked like this, without restricting the domain, and it had the inverse that went like that. Now, some of you would be saying, wait, do I just get to kind of flip this sideways? Yes, you do, but we'll get there a little bit later. So what you have here now is your horizontal line test. Horizontal line, horizontal line, horizontal line, horizontal line, pass, 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 pass. Yep, it's a function. Fail, 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 fail. Yep, it's not a function. I hope that this one example is enough. So when you have a function in front of you, You draw the horizontal lines mentally, draw the horizontal lines, and if it passes in every instance, well, guess what? You have an inverse function on the other end. But if it fails, like right there, if it fails on the horizontal line test, then you don't have the function on the other end. Isn't this cool? Hello?
Wait, for x squared, so okay, the first one I can see, that yes, that does. But for the second one, when you draw the horizontal lines, doesn't it still touch the graph though?
What do you mean? Are you talking about this picture here?
Yeah, and the one next to it.
Oh, this is an inverse. I'm not testing inverse. The horizontal line test is done on the original input function to tell us whether the output will be function or not,
Oh,
without
okay.
us even knowing what the output is. We have no clue what the output is. We only have the function right here. And I'm just looking at the function and I say, oh, it passed, so the inverse will be a function. Over here, I
Oh,
say, oh, it failed. The inverse will not be a function. So I don't know these graphs on the right per se, right? I don't know them. I just know the left side, and I just know that the left side passed or failed. That means that the inverse will be a function or will not be a function. And the convenience, right? The convenience is that I know what these graphs are, so I can quickly confirm what I found here immediately visually, right? Because horizontal line test on the original function is a vertical align test on the inverse. So you see that it is a function using the VLT, and you see it's not a function using a VLT.
oh, it
Vertical
has
line
to
test.
touch each of the points only once.
Yes, very good. Yes, 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 yes. So the function, right? The graph is the function if the vertical line crosses each point of the graph exactly once. If at any point in the domain crosses it twice, it's not a function. And that's it for the functions. But now we have inverse functions. So horizontal test on the original function will tell us whether its inverse is a function, which is kind of two-step procedure. So does this make sense now? Is it kind of unraveled a little bit?
I'm confused when you would use the vertical line test and when you'd use the horizontal line test.
All right, let's clear that up. Very good. Y equal x squared. Is it a function? Okay, to answer this, use vertical line test to check. Da, 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 da. La 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 la. Yes. And we're done. Y equal x squared is its inverse a function. Use HULT to check. La 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 la. Nope.
Wouldn't the inverse graph look different? Like, wouldn't it be on its side?
I'm not checking horizontal on the inverse. The purpose of the horizontal line test is to check on the original function without knowing or drawing the inverse.
Oh, okay. So you're doing this so you don't have to flip it and check.
There we go, my friend.
Gotcha. Oh, okay.
Very good. So both of these tests are done on the original function, on your f of x. Both of these tests are done. And the first one, the vertical line test, will tell you if that particular function is a function. I mean, if that expression is a function. And the horizontal line test will tell you if its inverse is a function. But they are both done on the original function. Are we all on the same page now? Crickets? Crickets? Crickets?
Yes.
Okay, good. Whew. For the moment, I thought I stayed alone. I started getting depressed and stuff. All right. Okay. The red color is coming up. Test if two functions are inverses of one another. There we go. Another. What? Well, I give you two random functions. F of x equals 3x plus 4, and g of x equals square root of x minus 3. Are they inverses of each other? Well, one way to figure it out is to actually find the inverse of f and then compare it to what you see with g. Right? And that's going to take us some annoyance. We have y equals 3x plus 4, x equals 3y plus 4, x minus 4 equals 3y, and then 3y equals x minus 4, and y equals x minus 4 over 3. So the inverse of f is actually x minus 4 over 3, so no, they're not inverses of each other. So that's one way to figure that question. But there is a much better way. Function composed with its inverse is equal to, well, you can write it this way as well, is equal to x. Also, inverse composed with a function is equal to this. Let's do the special box. Given two functions, if you do function composition between them, if the answer ends up being x, they are inverses of each other. Well, we can test that immediately with these two functions. Let's see, what was it, 3x plus 4? So my f of x was 3x plus 4, and my inverse of x was x minus 4 over 3. Let's find the function composition, meaning f plug in inverse. So here is my f. Here is me plugging in inverse. Remember how you replace every x of the first function with the function? We only had one x, so there you go. And now just follow the algebra. 3 and 3 will cancel. You get x minus 4 plus 4 equals x. Woohoo! So we just confirmed what we knew because we got this inverse from this function using the proper procedure. So we know it's an inverse. But we can also use the red formula here to confirm that. Now let's go the other way. Compose it backwards.
But don't you need to already know the inverse of that function to do this formula?
That's correct, yes. And remember what your problem was. I were given two I was given two functions to check if they are inverses of each other. So just do f of g, and you are not going to find x.
But don't we already know that g of x isn't the inverse of f of x because we found the inverse of f of x and it wasn't g of x?
That's true, but we know it because we wasted time to find the inverse. These formulas are used so you don't have to find the inverse.
Don't you need the inverse for the formula though?
Again, you are given two functions. And the way I solved it is I found the function and then I said, well, this is not the same here, right?
Yeah.
That's what I did. So that's how we knew that it was not, that f and g are not inverses, because these two are not the same. That's how we knew. But if nothing in a problem is given right there, like none of this stuff exists, okay? Gone. All I do is f of g, and when I find that it's not x, they are not inverses. I don't know what the inverses on individual functions are. I just know that these two f and g are not inverses of each other. That's the point of the calculation for this.
I get that, but when you scroll down, aren't you using the inverse in the form, like the part written in red? Didn't you find that by finding the inverse, and that's how you're doing the formula?
Mm-hmm. Yes.
So
and now I am understanding that we are talking about two different things now. Awesome. I'll answer your question when I finish this. I promise. We're talking about two different things. So let's just finish this line, and then I can answer your question finally. Now I got it, what you're asking. All right, so now we cancel these x's, these 4's, and we have our 3x over 3, and we got x again. So what we proved with this example is that these two are inverses of each other. So if the other question was f of x equals 3x plus 4 and g of x equals x minus 4 over 3, are they inverses? Well, because you were able to compose them and get x every time, you would answer yes. So the problem over here was the confusion with with me switching the problem to a different problem and not announcing it. So what you have seen from this thing from here, what you see from here all the way through here are two different problems. And that's my bad. I should have said that I switched the problem. So this is problem number 1, where I ask, are these inverses of each other? And the answer was no. And the way we answer this question is by actually finding the inverse of f and saying that's not the same as this g. So they're not inverses of each other. And then that problem is over. We're done.
Okay.
Done. And then I said there is a much faster, better way to check this than going through this calculation into f. And the way to check if two given functions are inverses of each other, so you have them already, if two given functions are inverses of each other, is to use the red stuff.
Now,
yes.
Are you using both of the formulas or just one of them?
Now we're going to go to where I should have gone, and I didn't, unfortunately. So instead of trying to prove to you that these formulas work, I should have actually done the original problem of f of 3x plus 4, sorry, f of x equals, and g of x equals root x minus 3. The way for us to check if two given functions are inverses of each other is to find the composition of them. So 3g plus 4 is 3 root x minus 3 plus 4, which is not equal to x. So no. F and G are not inverses.
Okay, I get it now.
So this is the problem. I messed up. Instead of solving the problem using the formulas, I went to show that formulas work on inverses instead of solving the problem with it and then talking, oh yeah, these formulas work, by the way, because if you actually take two functions that are inverses, here, look, it works.
Gotcha.
So are we okay now? Everybody's now?
Yeah, this makes sense.
Cool. Yep. Well, that's what happened when you have a mediocre instructor.
So we're just doing the function composition that we just learned last class, and if it doesn't come out to x, then that means they're not inverses. If it does come out to x,
Perfect.
they are.
Yep.
Okay.
Yep. Now I'm gonna just quickly jump over here and try to see. So on page 269, problems 1 through 10 say find f of g of x and g of f of x to check if the two given functions are inverses of each other. That's what you have. Like I'm reading that in a textbook. And then they give you a whole bunch of these f's and g's, and then you're just supposed to use the function composition to check if they are inverses of each other. So when you do function composition, if the function composition comes out as x, bueno. If the function composition is not x, no bueno. That's all. So let's take a look at problem number, I don't know, 6. I don't care. Pick any. So f of x equals 3x minus 7 and g of x equals x plus 3 divided by 7. Okay. Are these inverses of each other? So you have choice now. Do the function composition and see if it's x. And if it's not, they're not inverse. Or pick one of them, find the inverse through that algebraic process, and then visually compare inverse with g. You have two ways now to verify whether these two are inverses of each other. So obviously function composition will always be faster because we don't know how many algebraic steps we're going to have to solve that inverse all the way down. Function composition should always be like one line and you're done. So 3, stick in g minus 7. And the g is x plus 3 over 7. Well, they don't cancel. You get your 3x plus 9 over 7 minus 7. Well, that's not going to be x, no matter what you do. You can find common denominator. You can push this further if you don't see it. Minus 49 over 7. And then you have your 3x minus 40 over 7, and that's not x. So, nope. So you are given f and g, and you are asked if those two are inverses of each other. We cool now?
Sounds good.
Awesome. Well, you guys will have the homework is posted, as you know. You can enjoy this. Let's say bye to YouTube, our million viewers. Like, subscribe, and and hit the notification bell so every time I come online you can enjoy calculus.